So it's a pleasure to have Xinghao Qiao here from LSE, and he's going to be speaking about regression with dependent functional errors in predictors.
Thank you very much for the invitation. So today I'm going to talk about my recent work on the functional regression models. But we focus on two extensions on the traditional functional model. The first one is we relax the independence assumption. So we consider the functional data, but there will be some zero dependence across the curves. So secondly, we assume that the functional predictors are not fully observed. So instead, they are observed with some measurement error. And so this is a joint work with my PhD student, Cheng in LSE, and also Professor Shaojun from Renmin University of China. And so basically, first of all, we introduce the functional linear models and so some recent development and give a basic literature review. And then I will talk about the main idea of our approach and the estimation procedure. And then I'll talk about some computational issues, asymptotic results, and finally, I'll illustrate my approach through several simulation studies. So this is the basic introduction about the functional linear regression. So actually here we consider the most simple functional linear regression. So suppose that the response variable is a scalar variable, and the predictor is functional. So we call this functional regression to be the scalar functional regression model. Maybe I have a typo. But this is the most simple functional linear regression model, and so further extensions on the functional linear model can be the response variable can also be functional. So that means both the response variable and the predictors are functional. And with loss of generality, we assume that the response variable and the functional predictor, both of them are centered to have mean zero to facilitate our estimation procedure. So there's a rich literature on the functional linear regression models. So the most classical one from the chapter 12 to 16 of the Ramsey and Silverman's book. And then Hall, in their 2007 paper, they do a theoretical investigation about functional linear regression models. And later, Krempis, in their 2009 paper, they sort of relaxed the assumption by considering some incomplete observed functional data. And recently, there are some work on extending the functional linear regression model for the curve time series data. And
sorry, just a question. Is the marginal distribution of y and xt independent of t? Or is there some kind of stationarity here?
So here we just basically introduce the traditional functional linear regression model. So later I'm
so here it's IID.
Yeah, IID setting. So now we focus on IID setting. Later I'm going to talk about our situation. Okay. So the current literature focus on the IID functional data. However, it is possible that the functional data can be dependent. So the curves can also arise from segments of consecutive measurements over time. So some people call this type of data to be functional time series, so I prefer to call it curve time series. And this curve time series will violate the independence assumption, since the zero dependent structure across the curves will exist. So here I'm going to quote one of the Bassi and Yao's annals paper that, so one advantage to view the curve time series as a curve series is to accommodate some non-stationary features into non-stationary framework within the Hilbert space. So you can think about this type of functional data like the following. So you can observe the daily stock price. So across the day, so we can try, so within the day, we can consider the stock price as a curve. So this will be a functional data. And across the day, of course, there will be some dependent structure. So this can be a time series. So this type of data is called the curve time series. And examples will include a lot of curve time series data, like the daily curves of financial transaction data or the intraday electricity load curves. So, and how to use the functional linear regression model on the curved time series data is the one problem we are trying to investigate for. Okay, so the other way I'm going to talk about the functional regression with the error-in-predictor setting is that in practice, so the functional predictors are not fully observed. So instead, they might be observed with measurement error by the W here. So the W is actually the observed functional predictors, and X is actually the true signal predictors. So the E here is the error process. So basically we can assume that so W is actually our observed function data, but X is the curve of our interest, but it's not observable. But X and E, they can be assumed to be uncorrelated. So there's in the functional linear regression setting, there are also a rich literature on studying this error-in-predictor functional regression problems. So still the first work is by assuming that so we don't observe W, but also we observe the true signal, which is X. But that's not very practical situation because the curves might be contaminated by some measurement error. And in the later work, the authors consider the incomplete observed function data. So they assume that rather than observing X, they are actually observing W at a grid of time points. And so basically, based on their framework, they actually relies on a very strong assumption. So that the covariance of WT at uj and WT at uj prime is equal to the covariance operator of the true signals plus sigma square times indicator j not equal to j prime. So this can be understood like for j and for the j's time and j prime's time. For the same time, you have the measurement error, and for different times. So this term actually can be cancelled out. And there, people also make a very strong assumption like, so this is the covariance structure that you observe. And they assume that this true covariance structure of the true signal is actually smooth process. And so you can see here, this is actually a parametric model because the covariance structure of the error process take this form. So the way to fit this approach, model is you actually apply the non-smoothing approach on the off-diagonal elements of the row data of this covariance matrix. And then you get a smooth estimate, and then you can estimate both the first term and the second term. So as I mentioned, here the error process does not correspond to the fully non-parametric covariance structure. So we cannot say that this error process is truly functional. So we say error process truly functional if the underlying covariance structure is, we don't make any parametric assumption on that. But here we actually make a parametric assumption. Okay, so and the traditional way to deal with the fit the functional regression model here is actually so it's by the finite truncation idea. So the most naive approach is because this W is actually infinite dimensional. So we actually do some coupling law expansion on W based on the spectral decomposition of the covariance operator of W. And then we can, by some finite truncation, we can transfer the functional regression problem into the multivariate regression problem. However, this approach will fail to account for the contamination that will actually result in substantial estimation error because the covariance of the error term will not be 0. So later recently, the recent paper by CNP, they actually implement the regression collaboration approach with a matrix completion technique to separate the true signal from the observed predictor. So their approach is based on the assumption identifiable result like provided. So so real analytic for X, and so a banded covariance structure for E, then these X, the signal and the signal and error can be identified. But all of the work I mentioned here is actually developed under the independent assumption. And so here you can see, even if for the related work, the covariance structure of the error process still a banded covariance matrix, so it's sort of the parametric assumption. So what we consider here is actually we consider the more general functional regression setting. So we consider our regression with the dependent functional predictors, and the functional predictors are not fully observed. Actually, they are contaminated by the genuinely functional memory errors, which are the genuinely functional memory error. I mean the underlying covariance structure of the error process will not have any parametric assumption. So this is our model framework. So the first part is just the traditional scalar function regression. And secondly, so this the signal predictor is not actually observed. Instead, we observed the noise version. But here we make assumption that the error process a sequence of Y noise, such as expectation 0, and so the covariance operator is 0. So ETU and so this ETU and ESU will be 0 for any U and V provided T not equal to S. But for the case that T equal to S, this covariance operator can be non-zero. So actually, this is our model framework considered. So we don't make any independent assumption on X, but we actually assume that so this X and E actually are uncorrelated. So by having this assumption, so we can guarantee that so all the dynamic elements of the W will be incorporated into the true signal components, while all the Y noise elements will be absorbed into the error process. And by this kind of framework, we also assume that so the errors for the predictors are uncorrelated with both the true predictors at different legs and also the response variables, response errors. So here, this is the response error. So this is actually the model we consider. So actually, we assume we don't make any parametric assumption on the covariance structure of E here, but we assume that this E is actually a Y noise sequence. And we also assume some uncorrelation structure. Okay. So this is the model we consider. Okay, so let me first of all talk about this approach, our model and its relationship with the most popular Kahula domain approach, which is the typical approach deal with the functional regression problem. So before talk about that, let me start with some notation definition. Suppose for any integer k, we assume that the leg k autocovariance operator of x can be denoted as CKUV, which is the covariance of XTU and the covariance and xt plus k at time v. So then this might be a little bit not popular used, especially if k is greater than 0. But if k is 0, then this autocovariance operator will just be reduced to the typical covariance operator of the true functional predictors. So we assume that, so they actually, by having the square integral condition, then this random process can be expanded following the Kahula domain expansion by the following. So there's the j from 1 to infinity, and so this phi here is actually the principal component functions, and the cosine here is the xi here is actually the principal component scores. So it can be calculated as the following, and we assume that all the principal component scores are uncorrelated, and the variance of the principal component scores is equal to lambda j for the j's principal component scores. So this lambda j will actually be a decaying sequence. So that means for the first principal components, the lambda 1 is the largest. That will explain the largest variability of the data. And this approach is the typical approach used in the functional data literature. But it turns out that later I'm going to show you that this approach doesn't work in our model setting. So we assume that. So how to obtain the principal component function and the slopes? Here actually, we assume that here the eigenpairs lambda and phi. So the eigenvalue eigenfunction will be the eigenvalue eigenfunction of the covariance operator. And we assume that the lambda is followed from a decaying sequence, non-increasing sequence. Okay, so we define the xt is d-dimensional if all the top d eigenvalues, because the eigenvalue is a decaying sequence. So if all the top d eigenvalues are non-zero and d plus 1 eigenvalue is 0, then we say that xt is d-dimensional. So this is in the case that d is finite. For the truly functional object, d can be infinite. So that means all the eigenvalues will be non-zero. Okay. Okay. So then let's talk about the the problem. So in this functional regression problem, so we actually want to estimate the slope parameter, which is this beta function. Okay. So based on the observed data. So here we observe the response variable and the error contaminated functional predictors, so y and w here. So we want to, based on the information of y and w, estimate so beta here. Okay. So based on our assumption, we assume that all the k-length observed functional predictors are uncorrelated with the error term. And here, based on this result, so we can choose these variables to be the instrumental variables. So, but they are actually functional data, so we call them to be the functional instrumental variables. And based on this result, the population moment conditions will be the expectation of the error term of the response and wt plus k. So this will be equal to 0. And if you expanded this result into specific terms, then you can realize that, okay, because this error term will be y minus x beta, okay? So here we have a y here, and here we have so we should have an x beta here, but because we make some uncorrelated assumptions, so we can have this representation. Okay, so this representation is sort of familiar to some of you because you can realize that as some sort of so this if you understand this part as the linear regression, traditional linear regression. So this can be just understand as the x transpose y. So this is x transpose of x. So this is beta. So this is the typical normal equation, population normal equation in the multivariate setting. So now let's consider the situation special case if k is 0, which is a typical Cahulla-Levin-based truncation approach. Okay, and based on that, if k is 0, actually the covariance operator of the true of the observed functional predictor is equal to the covariance operator of the true predictors plus the covariance operator of the error term. Okay, so here, because this is something we are actually interested in, but this is something we observe. But this term is not necessarily 0 because if we want to develop a legitimate estimator, so we want to guarantee this term will be cancelled out. Otherwise, this will be the underlying bias term. And there are some discussion on how to eliminate the effect of this term, especially by Haas 2006 JSSB paper. They consider the separability of the C0 of the observed functional covariance operator by assuming that all the observed functional covariance are independent, and the error term will decay to 0 as n goes to infinity. But this is not a very realistic assumption because here, how can you guarantee as n large enough the error term will be very, very small?
What do you mean by separability?
So this term, separability, I mean,
Identifiability?
yeah, maybe,
Okay.
yeah. Okay, so actually we don't make any assumptions on the dependence of W, and we don't make any assumption on whether the error term will be decay at a certain speed or not. Okay, so so our approach is actually based on the simple fact that so remember here, if you see this normal equation, so W is the term we observe. But actually, we want this term to be the same as so the covariance of y and w should be equal to the covariance of w and x, because x is the curve of our interest. So we don't want to have any bias term. So by our assumption, we can guarantee the first result hold that the covariance of y and w will be equal to the covariance of y and x. So x is our true signal. And the second assumption, and the second result is, so because here you have this representation, this error, the covariance operator of the error process cannot be neglected because it's non-zero. But because we assume the zero-dependent structure, and for the lagged, I mean the autocovariance operator, so the covariance of Wt and Wt plus k will be equal to the true autocovariance operator for x. So based on this result, this error term actually will be cancelled out. So we just, based on these two results, we eliminate the impact from the noisy terms. Okay, and based on this result, so here in we actually developed a generalized method-of-moments approach. Okay, so here for some prescribed positive integer L, so L can be any positive integer, but L cannot be very large. Okay, I'm going to later talk about how to choose L in practice. And so actually we implement the GMM approach. So based on our moment condition here, and these two simple facts, so we want to minimize the distance between a moment condition for the L different moment conditions to 0. And distance is measured by this quadratic form. So, so here you can just understand this distance is the extension from the scalar setting to the functional domain. And so the middle term is actually the weight matrix. So it's not a scalar matrix, it's a functional matrix. So it's an L by L matrix, but each term is the covariance operator. So it's a L by L functional covariance operator based matrix. And a suitable choice for this functional matrix will satisfy the symmetry and the positive definiteness as what we require for the scalar matrix. And here, to simplify the calculation, we just assume that, so for k equal to L and u equal to v, this is 1, otherwise it's 0. And actually, we tried two different versions of this, but this will actually not affect the result too much. And if we try more generalized, like the two-step GMM, the improvement is not very large, but derivation is much more complicated. So we just want to simplify our derivation. So then actually, we have our target function we want to minimize is the following. So here, this is just a moment condition. So you have a L different moment condition, you take the square of it, take the integral, and you want to minimize this quadratic function with respect to beta. Okay, so how to minimize that? We just take the derivative with respect to beta. So beta here is a function. So in a similar way of the matrix calculus, we can have the functional calculus, functional derivatives, and then we can derive this. So we call this to be the GMM equation. And based on this equation, we have the first term and the second term multiplied by beta, take the integral should equal to 0. And this we can just assume that the first term is actually our function, so it's a function. And the second term, we can set it to be a k operator. But interestingly, it turns out that this k operator is just the operator that is used in Bastiat's Anno's paper. So they actually developed a dimension reduction approach for curved time series based on this non-negative autocovariance induced operator. So actually we don't realize the result, but actually after we have some deep thoughts on it, we realize that they should be they have some similarities and in their paper they studied the properties of this operator, okay? And substituting R and K in substituting relevant terms in equation 4 by R and K, then we can have this representation. And this representation is again something we are familiar with, because here you can just realize it to be the response variable, and here it's just so here you can understand as x transpose of y, and this is you can understand as x transpose of x if you study the multivariate linear regression and beta. So you can just solve beta from the normal equation. So we call this our functional representation of the normal equation. So under the population level, so our target is actually estimate based on our target is actually to solve beta based on this normal equation. Okay. And then the problem is that so this K is actually the covariance operator. If you want to solve it, then you might need to consider the inverse of K. Okay. So here we provide some discussion on the properties of the covariance operator of K, the operator K. So because assume that X is actually d-dimensional, so then follows from Bazia's paper that so K is actually, if X is d-dimensional, K will also have exactly d non-zero eigenvalues. So in a non-increasing order, and we assume that the spectral decomposition for that is the following. So theta is actually eigenvalue, phi is actually psi is actually the eigenvector, and the eigenpairs will satisfy this eigendecomposition, eigenfunction. Okay. So then under some conditions, we just want to take the inverse of this covariance operator, and take the integral with respect to R, and then based on the spectral decomposition, so our solution of beta will just be in the following form. So that's that's the solution under the population level. So then the question is, how can we calculate the inverse of a covariance operator? Is it invertible? So this is a typical problem in the functional analysis literature. And it turns out that the K is not generally invertible, but if we have some restriction on K, on the domain of K, such that we restrict the domain of K such that non-zero elements will be mapped into the zero members, then based on that, we can have the invertible property. So here we just consider non-space of K. So by consider kernel and also consider a complement of the space. So we call this to be the so K tilde is actually the K conditional on the complement of the non-space of K. So then by having this restricted condition, then we can just use the generalized inverse of K, we denote it as K inverse. So this will just correspond to the inverse of the restricted operator. Okay, so this is invertible. So this is the first technique we need to apply. And secondly, so if K is a bounded operator under the infinite dimensional setting, then the K inverse will not be a bounded operator. So how to understand that? If you consider the Hilbert-Schmidt norm of the K, so it's finite. So the sum of the eigenvalue will be finite. But if here you consider inverse of it, you consider the sum of the inverse of the eigenvalue. So that will actually make this term to be unbounded. So we know that for unbounded operator, it is discontinuous and cannot be estimated in a meaningful way. But good news for us is the inverse of operator does not necessarily always appeared associated with another functional operator. So then the composite functional operator can reasonably to be assumed to be bounded. So for example, another regression operator in a recent paper. So here we just assume that because we are not only interested in K inverse, but we're also interested in this integral. So we just assume that this integral to be bounded into the L2 sets. Then the result and the infinite dimensional setting that the GMM solution will exist and take the form of the following.
Can you remind me what R is?
R is something here. The covariance, so you can consider the covariance between y and some x, like you take the integral or something. Okay, so
R should depend on K, right?
R should be
On this index, on the leg.
yeah. So you consider all the legs information
Okay,
from
yeah.
1 to L. So
It depends on L.
it depends on
It's
L.
sum. No, it's
Sum, yes.
Okay.
So the reason why we don't use only one leg is because if we have more legs, we can have more stable estimate. We also try one leg, but the result is not very good. So I'll talk about that later. Okay, so then everything becomes straightforward. So we just need to provide the estimate for all the definitions we have. First of all, we need to estimate the leg K autocovariance operator. So this is just a natural estimator, and of course the covariance between Y and W, but also in the auto way. Okay, and similarly, the natural estimator for K will be the following. So you just substitute C by C hat. Okay, so then it can be written in terms of this form. And so especially for R, we can also have the formula for that. And after that, we perform the eigenanalysis on K hat, and then obtain the eigenpairs, estimated eigenpairs. Then we substitute the true eigenpairs by the estimated eigenpairs. And then if K is infinity, then we just take the finite truncation idea by only consider the first leading principal components, okay? But if D is smaller than infinity, then we will use some bootstrap approach to estimate D, which we denote the estimate to be D hat. So D and D hat will be equal to, will have a will be equal with a high probability. Okay, so this is our estimate.
So do you assume D is known?
So we
So do you know whether D is infinite or not? You have to test for it.
we only consider different cases, and for you mean in practice or
Yeah, in practice. So which of the two do you use?
so in practice, none of the functional data will be truly infinite dimensional.
Right.
So we just take the second one.
Okay.
You mean the observation wouldn't be infinite dimensional?
The observation. So actually, I think the first one is only for theoretical investigation, and because here we have we have the signal component, so the signal component can be reasonably assumed to be finite dimensional. So also we can extend the idea into the functional response setting. So we don't have time to cover that, so but it will work very well. Okay, in terms of the computation, it turns out that we assume that actually we have we have a lot of complicated calculations like here the integral part. So actually in practice we find like our estimate, because of the accumulated error, that will make our estimate to be undersmoothed. So actually in practice we can impose some sort of some form of smoothness by the basis function expansion. And here I just want, not going to talk about it in detail, but here you can just, so this is just a typical approach in the functional principal component analysis literature. So what you need to do is actually, if you obtain some non-smooth functions, so you can just apply, impose some form of smoothness by the basis function expansion idea and try to make it more smooth. And this further procedure will make our simulation result to be much better. I will talk about that later. Okay, so selection of tuning parameters. So we have 3 parameters we want to select, which is the first one is the leg length. So in practice, so we cannot have a very small number of L because like L is 1, then it will actually only based on just the one like information that will actually make the estimate to be not very stable. But L cannot be very large because most of the time the autocorrelation will be very small for the first several leg terms. And if you have so many legs, the accumulated error will make the estimate not very good. So in practice, we do a lot of experiments trying to investigate different values of L. But it turns out that L equal to 5 always give us good result. And there's extensive simulation studies in the non-functional setting in the Lens paper. And they also use 5 to 10 like to be the candidate value for L. And to select the D hat or M, so D hat is actually under the finite dimension setting, M is actually under the infinite dimension setting. So there are different approaches. First one is just to calculate the cumulative percentage variation. Say you calculate the top 3 eigenvalues. If they can explain more than 90% of the variability, then we just use top 3 eigenvalues. And also, you can use the eigenratio-based estimator, but this estimator is not very good, especially you have a small value. If you have small value divided by another small value, sometimes the eigenratio-based estimator will not be good enough. So there's a recent Statistical paper trying to investigate the special case of small value situation and have some nice result, but we haven't had a chance to apply that. And the last one is actually the bootstrap approach, which is introduced in the Garcia's paper. So actually, in our paper, we use this approach. And because in our simulation study, we only consider the finite dimensional setting. Like the signal can be 5-dimensional, 10-dimensional. So actually, we only consider finite dimensional setting. And for select J, so people can use the cross-validation approach. I'm not going to talk about the detail, but some people may argue that because this is time series data, how can you use the cross-validation? We do think that's an issue. We actually implement different versions of the cross-validation for time series data, but turns out that the improvement is not very large. So we just take the typical cross-validation approach, and the result is, I think, is good enough. So we don't spend a lot of time on how to use the time-dependent cross-validation approach to tune the parameters. Okay. Okay, so. So the bootstrap approach is actually we just want to test, okay? So whether the theta d plus 1 is 0 or not. So we'll reject this non-hypothesis if the estimated theta d plus 1 is greater than some critical value. So we summarize the procedure as the following. So suppose that we have estimated W hat, which can be represented by the following form, that eta is actually the estimated principal component scores. And the E here is actually the estimated residual. So what we do is actually we do the bootstrap on the residuals by draw from replacement from this E hat. And we generate some bootstrap sample of the E star. And then because we have W hat plus the E star will give us the bootstrap sample of W star. And based on W star, we can estimate the underlying K hat star. Everything is just the same. You just substitute the WT by WT star. Okay. So based on that, you can calculate the D plus 1 largest eigenvalue. And then we can just repeat step 2 and 3 many times and reject H0 if the event that theta hat D plus 1 is greater than theta star D plus 1. Okay. So this approach is not working very well in the small sample case, but it works very well in the large sample case. Actually, we also investigate other candidate approaches, but it turns out that especially for the large sample case, this approach is the provide the best result, and the other approach do not always provide very stable results. Okay, so so the cross-validation approach here is actually, I'm not going to talk about detail, but we just sequentially divide the data into like if J is 5, then 5 blockwise groups. Okay, and based on the validation set, we estimate the eigenvalues and eigenvectors, and say something. And then, so here, this is actually the estimated covariance operator on the validation set. And these are actually the approximation based on the training data set. So we want to minimize this mean cross-validate error. And in practice, so everything is functional. You just use you approximate the function by a vector, and these actually R2 norm will just be the Frobenius norm for the matrix. Okay, so asymptotic properties. So the first condition is the mixing condition, but it's only for technical reasons. We have this, and then we have the standard moment conditions for the scalar and functional term. We have the and also functional function regression. We have the moment condition on the errors, and also we have the moment condition on the two predictors. And we also have the eigenstructure of the K operator. Okay, so if D is finite, then you just assume that all the eigenvalues are different. If D goes infinity, then we assume that we have an eigengap. It's controlled by parameter alpha here. So alpha is the parameter controlled eigengap. If alpha is very large, the eigengap can be very small. Okay? If D is infinity, then not only we control the eigengap, but also we control the bias term, because here we use a finite truncation. Okay, and it turns out that this eigengap result will indicate that the J's eigenvalue will be bounded below by J to the power minus alpha. Okay, so alpha can also be understood as the parameter. So alpha large, then this eigenvalue will decay very fast to 0. Okay, and these conditions are very typical conditions in the existing literatures, and they actually are used to derive the convergence result of the estimated eigenpairs. And in the previous Barthias paper, they only consider the case that D is fixed, but now we extend it on the approaching infinite dimensional setting and the truly infinite dimensional setting. And also we have the bounding assumption on the composite function. These are the typical assumption in the functional regression literature. Okay, so these are the three results we have in the scalar for the scalar functional regression. So if D is fixed, then you get a parametric rate. Okay, if D goes infinity, then you have this rate. So that means if D is quite large, then you have a slower rate. Okay, so alpha is also determined by alpha. Alpha, remember, so alpha is the parameter to control the eigengap. If alpha is large, then we have a smaller eigengap. That will make the problem more challenging. That actually will have the result into the slower convergence rate. And for the infinite dimensional setting, of course, we have the variance and bias trade-off. The first term is the variance, and second term is the bias. And we will have some optimum truncated dimension. Okay. And we also investigate on the functional regression setting, but the technique is very similar, and we don't want to. And notation is much more complicated, so we don't want to waste our time to talk about the details. So I think I'm going to talk about the empirical studies, which I think that's the most interesting part of the talk, because we struggle a lot in doing the simulation at the early stage, but finally we figure out our problem. I will share some thoughts with you. First of all, talk about the simulation setting. We generate the W equal to the true signal plus the error term. So the signal term is the D-dimensional. With the basis function phi j here, and the error term is 10-dimensional with psi j as the eigenfunction. Okay, so because we here assume the zero dependent structure of the signal process, so we assume that this basis coefficient follows from AR1 model with underlying coefficients. So this coefficient is also taken from the Barthias paper. So typical assumption. Okay, so we generate our beta also based on the phi here. Okay, and the B can take the values of these values. So here we consider three different settings. So D can be 2, 4, and 6. Okay, so that's also the typical setting considered in Bastiat's paper. So, so if D is 2, then we only consider top 2 components. If D is 6, we consider all the components. And finally, we generate the response variable like the linear regression model framework here. Okay, so the first model we consider is also taken from Bastiat's paper, but we use the phi and psi, so different for they are different for the signal process and the error process. Okay, but they are actually not orthonormal. So that's the reason later we introduce the orthonormal basis. And the reason why we introduce the orthonormal basis is by having orthonormal basis, we can easily calculate the variance term explained by each component. Okay, so which will make our make us to have a deeper understanding about eigenstructure and which approach will be superior to the competitors in what cases. And here the first setting assumes the innovations are following IID setting, IID sample. And secondly, we have a very strange, innovation structure. But also we try the ID setting, but later I'm going to tell you why we have this setting. Okay? But this is just artificially created a simulation example to illustrate the superiority of our approach. Okay, so we try different approaches, and the first one is FPC plus least square. First of all, you use the principal component analysis to the dimension reduction, and then transfer the functional regression to the multivariate linear regression, and then apply least square. And also we can develop the regularized FPC approach, plus the least square. And also we applied, we do the dimension reduction on the functional data, but we implement the JMM type approach. And similarly, we can apply the Bastiat and Yao, the Ziegelman's paper dimension reduction technique developed for curve time series, but with the least square. But our approach is actually can be summarized as applying this Bastiat and Yao Ziegelman's paper plus the JMM. So our approach can be considered as a BYZ plus JMM. And also we developed the regularized version of the estimator. So you can see that by the regularized estimator, so our approach significantly improved the other approaches. So here we consider different settings, small sample size up to large sample size, small dimension up to large dimension. For the small sample size, you can realize here our regularized estimator is not very good, as good as the FPC plus least square. And the reason for that is, later we investigate is because the bootstrap approach is not very powerful. And this is the part we feel a little bit confused, and we don't know a very good way to how to select the two, the dimension of the signal components. But as you can see, as the sample size increases, especially for 800, so if D can be estimated reasonably well, then our estimator can, first of all, our non-regularized estimator is good enough. It's better than all the competing approaches. And the regularized version even improved almost like more than 50%. Okay, and for the other approaches, so we also, for example, for the principal component analysis, we also investigate different approaches, like say the bootstrap, the eigenratio, or setting up the threshold value to select the leading principal components. But it turns out that the approach we are using will provide the best result, but they still do not have very good results. Okay. Okay, so this is our graphical illustration about our estimate. So the black solid line is a true beta, and the right dashed line is our estimator, and the right solid line is our regularized estimator. And the other colors correspond to the competing approaches. It turns out that so here this is a high dimension, N is 800, D is 2. Then it turns out that our approach is much better than the other approaches, D equal to 2. And you can see that if you don't apply the regularization, the dashed line will sort of be under-smoothed. But after we have the regularization, we make it more smooth. And here, actually, it seems like they don't have very similar shape. The reason for that is because we replicate our simulation 100 times. So just to report the median estimate. So we rank them from smallest to the largest in terms of the square error, mean square error, and we just report the mean estimate. And so this is the case for D equal to 4. Our estimate is still better than the other approaches. And you can see that the dashed line is sort of under-smoothed. So D equal to 6 setting, so it still fit reasonably well. Okay, so then we say, because we don't select the D in a very meaningful way, so why not we just use the true value of D to estimate our result? And turns out that if we plug in the true value of D, then our estimator, here we get our estimator, is actually not as good as the FPC plus GMM approach, okay? But it's better. So, but if you just compare least square with GMM, here you can realize the FPC plus GMM is better than FPC plus least square, and here BYZ plus GMM is better than BYZ plus least square. So that means GMM always better than least square. The reason for that is because we take the advantage of having the lag term to eliminate the measurement errors. So, but why is our approach is not as good as principal components plus the GMM? It's sort of strange. But the reason for that is because actually later we try to investigate the eigenstructure of our simulation model. So so actually it turns out that the signal component identified the PCA and BYZ are actually the same. So see next page. So here, first of all, we focus on model 2, but we still focus on the ID innovations with the constant variance term. So for example, if D is 2, then we have 10 components. The first 2 are signal components, and we have the 10 error components. We consider sum and cumulative percentage variability. So our approach can always identify the right points, the right numbers, which the top 2 signals will be identified. But if you use the principal components, although you actually you're actually based on the variance explained by each individual component, but you can actually calculate the variance explained by each individual component. So you can also realize that the first component still have the largest variance, and second component have the second largest variance. So that means our approach and the PC approach will identify the same components. So similarly, especially in this setting, so the PCA and our approach will give the same result in identifying the correct components. But then we try to make it more complicated. So we change the eigenstructure of the error term by not having the constant variance. We can see it here, still the first 2, so actually here we just ranked the variance of the sum of the signal and the error. So we can see that, especially for the first case, 1 and 2 have the largest variance. But for the second case, D equal to 4, 1, 2, and the 7th component, 8th component will have the largest variance. So that means by the PCA, that will select the component 1, 2, 7, and 8. So that's not correct. But our approach, we can still select 1, 2, 3, and 4. Okay. And similarly here, by using the PCA, that will select 1, 2, 3, 7, 8, 9. But our approach can still select 1, 2, 3, 4, 5, 6. And the reason for that is because the different approaches is based on different results. The PCA is based on minimizing the variance. Here, we actually use the information about the zero dependence. So especially under this simulation setting, we can actually improve our results.
Sorry, just a question. The subspace that is estimated is random. So what do you mean by saying that your approach selects PC 1, 2, 3, and 4?
We assume that under the population level, so we can calculate the exact number. Okay. So we don't have any randomness here.
Okay.
So because this is just for us to understand the eigenstructure, so we understand everything in the population level.
Okay.
So everything can be calculated. So that's a theoretical result. So let's see what happens for the practical result. So actually what happens under the model 2 practically, so also under the true value of D, so these are actually the results in the population level. Here we actually we estimate each component. So you can see that, so two versions of approach are much better than all the competitors. And it's reasonable because we specially designed this artificially created example that our approach will be much better than the other approach because we use the information about the zero dependence. They use the information about the variance. And I think the zero dependence information is more important in the time series literature because sometimes the error can be very large. How can you use the variance term for time series data? And it turns out that our approach is much better than the competing approaches, and regularized approach even improve the results. And also we see the graphical result. So the true result, and we have our estimate is much better than the other approaches. So in the paper we also report the similar table like the following by not having the true D, but having the estimated value of D. And we still get a very similar result. So that means our result is much better. I think it's more relevant in the time series literature. Okay, I think that's all the relevant work about my presentation. Thank you very much.
Any further questions?
So I have one question. Can you go back to slide 12? So I'm a bit puzzled by the assumption in functional data when people assume that for a given sample size, D is finite, and then let D tend to infinity. Because for a given sample size, I agree that for realization, it is finite dimensional, but it's on a subspace that is random.
Mm-hmm.
So, what is your justification for using that kind of asymptotics? Because when you assume that D is finite for a given sample size, you're assuming that your realizations are in a finite dimensional space that is non-random.
Yes.
So in some sense, you're translating your problem into a P and N tending to infinity high dimensional setting.
Yeah. So I classify the three setting I consider as a fixed dimension, high dimensional, and infinite dimensional. And I agree with you, which I don't like the second situation, like make D finite but approaching infinity dimensional. So I think the in practice, of course, the D can be quite small. That's only for the theoretical results. So when I read another paper, I consider the infinite dimension. So the high dimension. So your question is, so D is actually, so the second situation I consider is a high dimensional setting, which should not be classified as a functional setting. So functional setting will only be the third case or the first case.
Okay. I have other questions, but I don't want to monopolize them.
Go for it.
Okay. So can you go to slide 26? So essentially what III is saying is that you don't have a consistent estimate, right? Because M, what is M again?
Is the truncation, truncated dimension.
Truncated dimension. So what I know is usually people use some kind of regularization of, so they don't use generalized inverses, but they use a regularized version of the matrix, the operator they want to invert. Because essentially what you're assuming here is that your signal.
You mean the infinite dimensional setting? Finite dimensional
Yeah,
setting, we don't have the
the
problem.
infinite dimensional setting. Do you have any idea of how, have you investigated the regularized version where you add some kind of ridge or some kind of Tikhonov regularization?
No, we haven't seen. And so I think this result is based on the Peter Haas, the 2007 paper. Some similar results like the third one.
Okay.
And the eigenstructure assumption is also similar to their paper.
Yeah.
Remind us what the gamma is again.
Gamma is actually gamma is actually control the truncation error. Just,
Oh, it's straight up from the answer.
yes.
Good, okay, thank you very much. And Xinghao, you're on cake duty today.